In this video, we're going to look at some example problems of analyzing IR spectra. Okay, in each one of these examples, we're going to be given an IR spectra and then some molecules that we want to match to our IR spectra. And so what I've done in all of these examples is I've gone ahead and drawn my lines. And this is the first thing I'd recommend you do. Right, go ahead and draw in a line at 1500 wave numbers and another line at 3000 wave numbers. Right, and so anything to the right of the line, right, this is the fingerprint region. We're primarily going to ignore this section. We're going to focus on the diagnostic region above 1500 wave numbers. Right, and then this line at 3000, right, we're very often going to have a peak just under 3000, and these are CH stretches from sp3 hybridized carbon atoms. Right, what we're looking for in this region is double bonds at the lower frequencies, triple bonds at the higher frequencies, and then above 3000 wave numbers, we're looking for other hydrogen stretches. So typically, these are going to be oxygen, hydrogen, nitrogen, or sp2 hybridized CH stretches or sp hybridized CH stretches. And so I have a cheat sheet posted on D2L, which has the things that I'm looking for. I don't necessarily go in order when I'm trying to identify the different peaks, right? And in this case, right, the first thing that jumps out at me is this really big, broad peak centered around 3300, 3400 wave numbers. This is very characteristic of an OH group, right? So this is the OH stretch that we're looking at. So I almost certainly have an alcohol in my compound. So based on that, I can probably eliminate my compound with the carbonyl. Plus, with that, if I'd had a carbon-oxygen double bond, I'd have expected a big peak here around 1700, maybe high 1600 wave numbers. So now to differentiate between the two alcohols, right, the big difference in terms of functional groups is this one has a carbon-carbon double bond. And so I'd expect to see a peak in this region for a carbon-carbon double bond. So this could be it, but usually the peak, it has a little bit more intensity and it's a little bit more narrow. So that could be a carbon-carbon double bond. What I'd also expect when I have a carbon-carbon double bond with hydrogens coming off is that should shift one of the CH stretches above 3000 wave number. So that's why we put in this line here at 3000. If we have things just below 3000, those are probably sp3 hybridized carbons. If I had an sp2 hybridized carbon CH stretch, I'd expect that to be a little bit above 3000 wave numbers, and I don't see that. So this doesn't really look like a carbon-carbon double bond peak, and I don't have the sp2 CH stretch out here. So that leads me to assign this spectrum to this molecule. All right, here's another example, right? And so there are a couple things when I'm comparing this spectra to these compounds. First of all, I don't have a big OH peak here, so it's probably not either one of these two. And right, I have this nice big high intensity peak at around a little over 1700 wave numbers, and this is exactly characteristic of a carbon-oxygen double bond. So based on my choices, right, this is almost certainly the molecule. All right, and we go to the third spectra. So again, right, I've got this very characteristic OH peak. And then now I do have a peak. This is probably my carbon-carbon double bond. And right, I've got this CH stretch above 3000 wave numbers. And so this is probably my sp2 hybridized carbon CH stretch. And so this spectrum matches with this molecule. All right, here's a new set of molecules. And so again, right, we always want to mark our 1500 and 3000 wave numbers. And the first thing that jumps out at me is I see this double peak here at about 3400 wave numbers. And so this is a good indication that I probably have an NH2 group. And there's not much else going on in the spectra. I've got some CH stretches. I've got some other little peaks. Not sure what they are, right? But the presence of the primary amine, or the NH2, right, this is almost certainly the molecule that matches with that spectra. All right, in this spectra, there's not a whole heck of a lot going on. I've got some CH stretches in this region, right? There's nothing else really in the diagnostic region. And so when I look at the molecules that this could potentially be, right, we've already kind of eliminated this guy. Right, carboxylic acids are very distinct. Right, for carboxylic acid, I should have a broad, sort of hairy beard type thing in this region, which I do not have. So it's probably not the carboxylic acid. Right, so now I've got these two alkynes. Now this alkyne has a hydrogen attached here. Right, and so for this molecule, I'd expect that sp hybridized carbon CH stretch to be somewhere around 3200, 3300 wave numbers. I don't have any peaks there. This alkyne is not symmetric, so I'd expect to have a carbon-carbon triple bond somewhere here above 2000 wave numbers. So I don't like this guy. And when I look at this, right, there aren't hydrogens attached to the sp hybridized carbons, so that would explain why I'm not seeing a peak out here. And then this molecule is very symmetric. If you remember, for a particular vibration in a molecule to be IR active, when that stretch happens, we've got to change the dipole moment of the molecule. And because this molecule is so symmetric, I don't think this carbon-carbon stretch is going to do much to change the dipole moment. And so that would explain why we're not seeing a carbon-carbon triple bond peak. So, kind of based on the process of elimination, I think we'd go with this molecule. Okay, here's yet another spectrum. And the first thing I notice about this, right, I have the very broad peak, centered at about 3000 wave numbers. And, right, sometimes people describe this as the hairy beard. And this is where the OH from a carboxylic acid, right, where this stretch is overlapping with other CH stretches in the molecule. And so we get this large, broad peak that people describe as the hairy beard. And so this is a dead giveaway that I've got a carboxylic acid. And so the only carboxylic acid we have among our choices is this molecule here. And the other thing to notice about the carboxylic acid, right, we also have the big high-intensity peak around 1700 wave numbers, right, and that's the CO stretch in the carboxylic acid. So when you have the big, broad, hairy beard and the CO stretch at about 1700 wave numbers, right, that's the signature that we're dealing with the carboxylic acid. Okay, the final spectra here, and so when I look in the double bond, triple bond region, right, about 2100, 2200 wave numbers, I've got a peak, right, so this is probably a triple bond, and then this peak here at about 3300 wave numbers, this is what we'd expect to find if I have a CH stretch from an sp hybridized carbon. So by comparing this peak in the triple bond region to what I'd expect from a hydrogen coming off a triple bond, we can match that spectrum with the molecule on the left. So there are a ton more example practice problems on assigning IR spectra posted on D2L, so I encourage you to give some of those a try. The main thing on getting good at assigning these spectra is to just do a lot of practice.